Hi students, welcome to Year 10 Science and the space topic. This is video number 7 and we're going to just briefly touch on this idea of gravitational attraction. What's important for you to understand in terms of application in this component of the Year 10 physics is the gravitational attraction between two masses. Now we do have a mathematical expression for this, and it's one of Newton's laws, in which we look at the force of attraction being directly proportional to, in actual fact, equal to a gravitational constant multiplied by the two masses, mass 1 times mass 2, and divided by the distance between each of these two squared. Often you'll find this written as r squared, but that's okay. This is the mathematical expression, and so you can substitute values in for the mass of one object. Let's say this is the Earth, and let's say the second object is the Sun, and you can work out using the gravitational constant, knowing what the distance, which is often the radius of the orbit between the Earth and the Sun is, and then you can work out what the size of the force of the gravitational attraction is between these two bodies. This is what the second of these dot points basically says in a qualitative fashion. That is, the force between two masses is proportional to the size of the masses and inversely proportional to the square of the distance between them. What does this mean? Well, we have two masses here. We know that from Newton's first law that there are zero forces. So if there's no net force, there's no change in the motion. Now that doesn't mean there's zero motion. It could mean that an object is just carrying on moving at a constant velocity. But one of the problems that we have is if this object is actually orbiting another object, such as the Earth orbiting the Sun, and I am kind of simplifying this down to being perfect circles. We know they're ellipses, thanks to Kepler. But to just look at it in simple terms at the moment, what we would say is that because the object, the Earth, is rotating around the Sun, then it is going to, as a result of that, have a force, a net force acting on it. In fact, the net force that's acting on it is going to actually act to accelerate the object towards the Sun. So it's actually then an application of Newton's second law, which is if there is one force, then the force that is causing the motion is going to be proportional to the acceleration of the motion. So we express Newton's second law as the formula F equals ma. In this case, the a is the acceleration due to gravity. So if the force is the gravitational force, then the mass is the object multiplied by the gravitational acceleration that's causing it. And so this object will move in a circle. I've drawn it both ways, but it doesn't really matter which way it goes. We know that whichever way it is going, if it is moving in a straight line, the acceleration towards the Sun will pull it off that straight line, and therefore it'll move in a curved path. As long as it's got a high enough speed, it'll remain in that path pretty much forever. The only time it won't is if the speed changes, and therefore the angle can therefore change, which could either have the object moving out of the orbit of the Sun or actually coming closer and closer to the Sun. Any two objects in space are going to exert a gravitational force between them, but one thing we know about the gravitational forces is that they're very small. It is one of the things we do know. There are quite a few things we don't know about gravitational forces between two masses. But what you can do is try and resolve them in the same way that you have using Newton's three laws. And of course Newton's third law I haven't mentioned there, but that's the equal and opposite. And all that's saying is that if the Sun exerts a force on the Earth in this direction, then the Earth is also exerting an equal and opposite force on the Sun. So why they crash into each other? It's because of the difference in their masses. So the mass of the Earth is much smaller than the mass of the Sun, and therefore its acceleration is much larger proportionately. And also because of the fact that they have different velocities, and that's therefore going to change how that velocity continues to change as that force continues to act. Keep in mind Newton's 3 laws as you're trying to analyse the way that objects exert gravitational forces on each other. We simplify all of this down to say that if force is equal to mass times acceleration, then if the acceleration is gravity, that is acceleration due to gravity, then the force is a weight force, W equals mg. Now there's a tiny complication. There is a tiny complication when you are looking at gravity, because Einstein's equations, particularly his work on relativity, kind of messed us up a bit. The most important thing to remember about Einstein is his famous equation, E equals mc squared, which everyone knows, but basically means that there is some interaction or interactability, interchangeability between energy and mass. This is what powers the stars like the sun, but it also means that there is a way of linking energy like light energy to a gravitational effect. And this is one of the things that Einstein predicted, which was subsequently later found to actually be the case. And that is that very, very large objects like the sun create a curvature in the space-time continuum, if you like. And as a result, the path of the light can actually be curved by that gravitational field. As long as the gravitational field is large enough, the light can be bent, and so it means that we can see, and we've only been able to do this by looking at stars behind the sun during things like an eclipse, because the sun is so bright that comparatively any other stars are so far away, even if they're brighter, we just can't see them against the brightness that we get from the sun. So this is a variation. It's where our model breaks down a little bit in terms of the fact that gravity is a force between two objects that have mass. Well, mostly, but not always. And this is one of the exciting things about science, is that as we find new data, we have to just slightly modify our models, and we keep that in mind as we continue to have a look at space. Thanks for watching.